So far we have seen transformers being used for stepping up or stepping down voltages for supplying power to different types of loads. For example, a 3-phase transformer can be connected like this. For stepping up or stepping down the voltage to supply a load. So, this is, let us say, from high voltage side to low voltage side and vice versa. Now, in many cases it becomes necessary to measure the line voltage or the current flowing through the line. Ordinarily, one would expect to put a voltmeter and maybe in series a ammeter, or if you have to measure power, then possibly 2 wattmeters. For 2 wattmeter method of power measurement should be connected. However, in power transmission, this line voltage can be in excess of 200 kilovolt. This current can be in excess of several kiloamperes. So, instruments which can measure directly that kind of voltage or current are not available. Even if they are made available, working them with at such high voltages or currents is not desirable from the safety point of view. Hence, it is necessary to reduce these voltage and current magnitudes in order to bring them to the level where they can be safely measured using again transformers. These are called instrument transformers. Instrument transformers, there are two types. One is used to reduce the voltage level and hence called the potential transformer or the PT. This is the PT. To the secondary of which we can connect the voltmeter. It steps down the voltage, let us say, from some 200 kilovolt to maybe to 220 volts, or more often than not 110 volts. And a current transformer that steps down the current to which a ammeter can be connected to a much lower value of the ratio of 100 or even more. So, this is called the current transformer, or in short the CT. Now, the working principle of these transformers are similar to normal single phase transformers. However, special care has to be taken so that the voltage appearing across the voltmeter here or the current flowing through the ammeter here are in proportion to and in phase with the high voltage side or high current side voltages and currents. Normally, these transformers will be loaded with the measuring coils of the instruments. The potential transformer will be connected to a voltmeter, whereas the current transformer will be connected to a ammeter. So, a potential transformer will work almost at no load or at very light load. Similarly, the current transformer secondary will always be almost short circuited. So, let us see what type of precaution or what type of constructional specialties are needed to make this transformer. Let us take up the case of a potential transformer first. As the name suggests, a potential transformer is used to step down a high primary side voltage to a lower voltage of the range of 110 volts and is loaded usually with a current pressure voltmeter or the pressure coil of a wattmeter, both of which has very large impedance. So, let us say the turns ratio of this is N1 to N2. The equivalent circuit of this PT referred to the high voltage side will be something like the magnetization branch, this is R1, this is Jx1, this is R0 Jxm, this is the primary side line voltage V1, this is R2 dash, this is Jx2 dash, and this is the RL dash, which is the resistance of the voltmeter. Obviously, it should be noted that the voltmeter resistance is very large. The resistance of the voltmeter is very large, and hence the reflected resistance of the voltmeter can be comparable to the magnetization branch. Hence, it is necessary that the magnetization branch impedance of a potential transformer be very large. So, special care should be taken to make sure that the magnetization current of a PT is very small. Even then, when the magnetization impedance is small, it cannot be made lower than a limit. There will be some drop in the series impedances. Hence, we know that the output voltage presented to the load will differ from the value N2 by N1 into V1, V2 dash under the applied load will not usually be N2 by N1 into V1, both the magnitude and the phase angle of V2 dash will be different from this quantity. This is the ideal voltage that the voltmeter should have measured. However, due to the presence of the magnetization current as well as the series impedances, the actual voltage presented to the voltmeter will be different from its nominal value, and the actual voltage will in fact depend on the voltmeter or the load connected to the PT. Therefore, few things are in order. First of all, the magnetizing impedance of the PT should be very small. Second, its leakage impedances should also be very small, so that the regulation of the CT is almost 0. Third, it is desirable that a PT be matched with a measuring instrument. That is, if a PT needs to be calibrated, when you connect a voltmeter, you must calibrate the actual voltage and the voltage measured. So, it is necessary that a PT is used with a particular voltmeter, so that the current drawn by the meter does not change. Even then, it will change to some extent as V1 changes, but at least if we can reduce this, the regulation will be negligible. Hence, a PT series impedance will be very close to 0. It is imperative that the secondary of the PT should never even accidentally be short circuited, because then a very large current will flow, its impedance is almost 0 and will destroy the instrument. So, let us see what will be the relationship between the voltage V2 dash and V1. Let us say this is the PT equivalent circuit is somewhat like this. Let us say this is V2 dash. A voltmeter will almost appear as a resistive load. So, this is I2 dash, hence the no load voltage E1 will be V2 dash plus I2 dash R2 dash. This will be the no load voltage V1 or E1. The no load current will lag E1 by almost 90 degree and should be very small compared to load current. So, this will be the current I1 drawn by the PT primary, and the voltage V1 will be E1 plus I1 R1 plus J X1. This is the angle, this is the voltage V1. So, we see that because of the impedance drop V2 dash is not equal to V1, mod of V2 dash is not equal to V1, and the angle between V2 dash and V1 is also not 0. Hence, in voltage measurement there will be a error introduced due to the series impedance, and while power measurement not only the magnitude, but the phase angle error between V1 and V2 dash will become important. So, constructional features should address these problems. So, one should make sure that the no load current is very small, as well as the series impedances of the potential transformer are very small. For the current transformer, what normally is done is that the current carrying conductor itself or the line itself acts as a primary. This is normally passes through a magnetic core, the current carrying primary, and the secondary is wound on the magnetic core, to which a ammeter is connected. So, if we draw the equivalent circuit of a CT or a current transformer, it will be somewhat like the primary of the CT is in series with the line. Hence, this is the primary of the CT. This is the magnetization branch of the CT. Refer to the primary side. This is the connected to the load. This is supply. This is R0, this is JXM, this is R dash JX dash, this is RL dash, this is XL dash. Few things to note. First of all, the load current IL flowing here and the IL dash flowing here should be related by the ratio, ideally should be related by N1 IL equal to N2 IL dash, or IL dash should be equal to N1 by N2 into IL. However, that does not happen because the magnetization branch of the CT shunts a part of the current I0. Hence, again it is important that the magnetization branch impedance of the CT be negligible compared to the rest of the impedance, that is the series impedance plus the load impedance. So, it is necessary that a CT magnetization impedance be kept low. However, there is another important point here. It can be seen that even by accident, if the load is open circuited, then a relatively large magnetization branch impedance is put in series with the line, but even then that impedance is small compared to the load. Hence, this impedance does not affect the load current much, but what it does is the voltage across the CT, voltage drop across the CT increases very much, and along with that the flux density in the CT and the CT core saturate. Once it saturates, its properties changes, and hence that CT cannot be used any longer. So, care should be taken that a CT is not CT secondary is when the current is flowing through the primary, the secondary of the CT should not be open circuited even accidentally. Another important point for CT is that unlike a potential transformer, in a potential transformer the applied voltage to the primary remain more or less constant, varying within nominal range. Hence, this transformer can be designed in the manner similar to normal transformers for power application. However, for a CT, the voltage applied across the primary of the CT depends on the multiple product of the load current and the meter instrument impedance. If we use the same meter, then this impedance will remain constant. Even then, the voltage applied across a CT is proportional to the current. Hence, a CT always operates at a variable applied voltage and hence at variable flux density. Therefore, in order to have a linear or a fixed relationship, it is necessary that the CT operates in the linear region of the BH characteristics of the material, so that the impedances does not depend exactly on the applied voltage, and a linear circuit model can be used for a CT. If we try to draw the phasor diagram of a CT, this is the this is the series impedance of the CT itself, and this is the impedance of the instrument, maybe a ammeter or a the current coil of a wattmeter. This current is IL dash. To draw the phasor diagram, let us say this is IL dash, so the voltage E1 will be IL dash into the total impedance IL dash into RL dash plus RR dash plus IL dash into XL dash J IL dash XL dash plus X dash. So, this is the potential E1, the no load current will be almost at 90 degree with E1 this is I0, hence this will be the current IL. Again we see that the current IL is not equal to N2 by N1 IL dash, or IL dash is not equal to N1 by N2 into IL. It will depend on the relative magnitude of IL and I0. In order for this current to be, this calibration to hold, it is necessary also to make the CT magnetization branch, impedance of the CT magnetization branch as high as possible. Otherwise, it will introduce both magnitude error and the phase error. For current measurement, the magnitude error only is important, but when you want to measure power delivered to a to a load using potential and current transformer, in addition to the magnitude error, we should also take care of the phase error introduced by both these transformers. We will see this with the help of an example. Let us say I have a 11 kV source, 11 kV 50 hertz source, and it is supplying power to a load. I want to measure this power using a wattmeter and a potential transformer, using a CT, PT and potential and a wattmeter. So, what I will do, that I will have a PT connected here, as well as I will have a CT connected here. The wattmeter current coil will be, this is the CT, this is the PT, wattmeter current coil, this is the current coil of the wattmeter, and the potential coil of the wattmeter will be connected across the potential coil of the wattmeter will be connected across the PT of the PT secondary. So, the data is something like this. The PT data turns ratio, that is N1 is to N2, N1 N2, this is equal to 100 is to 1. This is the nominal conversion ratio also. So, HV side resistance is 7.5 kilo ohm. HV side reactance equal to 8 kilo ohm. LV side reactance equal to 0.65 ohm. LV side resistance equal to 0.6 ohm. And no load input power of the PT is 20 watt at 0.4 lagging PF with rated voltage on the HV side. The CT data are similar. Turns ratio is 2:100. The series impedance, that is R plus Jx, this is referred to instrument side. This is 1.05 plus J 0.3 ohm. Magnetizing ampere turns is 40. Iron loss ampere turns is 30. The wattmeter data the resistance of the potential coil is 20 kilo ohm, whereas the impedance of the current coil is this. Now, let us say the source is supplying ampere at 0.9 lagging PF and at rated voltage, that is at 11 kV. Question is what will be the reading of this wattmeter, how much power will the wattmeter read? Let us try to find out. Now, for the PT, as we have seen, the equivalent circuit looks somewhat like this, that is the equivalent circuit of a normal transformer. This is for the PT. this is R1 dash, the voltage applied is V1 dash, J x1 dash, this is R2, this is J x2, this is RL, this is the voltage V0 that will be read by the potential coil of the wattmeter. Now, what is R1 dash? From the given data, R1 dash comes to 7.5 kilowatt divided by turns ratio square referred to the meter side. This is 0.75 ohm. Similarly, x1 dash comes to 0.8 ohm. R0 dash referred to the meter side will come to, it is mentioned that it is 20 watt at when rated voltage was applied to the primary side, hence the secondary voltage was also rated. So, referred to the secondary side, R0 dash is 110 square by 20, that gives you 605 ohm, and xm dash equal to R0 dash by 1050, this comes to 264 ohm. The resistance R2 equal to 0.6 ohm, X2 equal to 0.65 ohm, and RL equal to 20 kilo ohm. Now, we can draw a Thevenin equivalent circuit of the PT equivalent circuit across the meter terminal. This will look somewhat like a Thevenin impedance ZTH V1 double dash RL, whereas this is V0. Obviously, V1 double dash the Thevenin voltage will be same as the voltage coming here, divided by R0 double dash J x n dash plus R1 dash plus J x1 dash into V1 dash. This comes to, with when we substitute the values V1 and taking V1 dash to be 110, comes to 109.53 angle of 0.0 0.866 degrees, and Z Thevenin, which is given by R2 plus J X2 plus R0 dashed parallel J Xm dash parallel R1 plus J R1 dash plus J X1 dash. This comes to 1.0919 angle 46.934 degrees. Hence, the voltage V0 will be RL divided by RL plus Z Thevenin into V1 double dash and this comes to 109.526 angle 0.0843 degree. This is the voltage that will be applied across the pressure coil of the wattmeter instead of actual 110 angle 0. This is the voltage that will be applied. So, both there is a magnitude and a phase error. Now, for the CT, what is the CT impedance referred to the supply side, that is ZCT dash equal to 2 by 100, which is the turns ratio square into the impedance is given referred to the meter side 1.05 plus J 0.3 ohm. This comes to 4.2 plus J 1.2 into 10 to the power minus 4 ohm. Similarly, the impedance of the wattmeter current coil referred to the supply side will be 2 by 100 square into 0.6 plus 0.3 ohm. This will come to 2.4 plus J 1.2 into 10 to the power minus 4 ohm. The magnetization current referred to the supply side to be magnetization ampere turns divided by turns on the supply side by 2. This will be equal to 20 amperes, and the iron loss is 30 ampere turns by 2, that is equal to 15 amperes. So, the equivalent circuit of the CT looks somewhat like this. this current, the total current flowing is I L equal to 500 amperes, this current is I C, this current is I M, the current flowing through the CT is to the wattmeter pressure coil, current coil is I 2 dash. Now, we can draw the phasor diagram. We take I C to be this current and this is the current I M, they are at right angles, and then the voltage across this combination is in phase with I C into R 0 and hence with I C. So, voltage across this branch is in this direction. Hence, we can draw the current drawn by this circuit. The angle of that current will be the angle of the sum of these impedances. So, let us say this will be the angle, this will be the current I 2 dash whose magnitude we still do not know, but we know this angle. This angle is theta m comes to 19.98 degree. This is the angle of the sum of these impedances. However, then the total current I L should be the sum of I C plus I M plus I 2 dashed, this will be I L. We know this magnitude is 500 ampere. So, let us say this angle is delta. And this angle is phi. Now, from this phasor diagram, we can write that 500, this is the magnitude 500, cos phi equal to I C plus I 2 dash cos theta m and also 500 sin phi equal to I m plus I 2 dashed sin theta m. Therefore, 500 square equal to I C square plus I m square plus I 2 dash square plus 2 I 2 dash IC cos theta m plus IM sin theta m. Or from this equation we can simplify it to read I2 dash square plus, since all other values, for example, theta m, IC and IM are known, 41.861 I2 dash minus 249375 equal to 0. This gives the meter current referred to the supply side I2 dash to be equal to 478.883 amperes. Hence, the actual current I2 flowing through the meter is 2 I2 dash by 100. That comes to 9.57766 ampere. The angle phi comes to be 21.54925 degrees, and the angle delta, which is phi minus theta m, this comes to 1.56614 degrees. The angle between supply voltage and supply current is theta L, which is cos inverse 0.9, which is 25.842 degrees. The angle between V0, that is the voltage across the pressure coil of the wattmeter, and I2 is theta W, which is theta L, plus the voltage's angle is 0.0843 degrees minus delta. This comes to equal to 24.36 degrees, whereas magnitude of V0 is 109.526 volts and I2 is equal to 9.57766 ampere. So, the power read by the wattmeter is V0 I2 cos of theta W. This comes to 955.6113 watts. So, multiplying by the nominal CT and PT ratio, the wattmeter reading will be 100 into 50 into W dash, that is equal to 4778 kilowatt, whereas the actual power is 11 into 10 to the power 3 into 500 into 0.9 W load. This comes to 4950 watts. So, the percentage error due to this is WL minus WM by WL into 100. This comes to 3.47%, which is due to both angle error and the magnitude error of the CT and the PT respectively. Thank you.